Welcome back everyone. In this lecture we will continue with the Fourier analysis on finite groups. So let us first understand the group algebra CG. So recall the convolution product that we defined on CG. So CG is the space of C valued functions from G, and we defined the convolution product. So given Fg in CG, so f star g of x is defined to be the summation f of x y inverse g of y y in g. So this is the product that we defined. So we claim that indeed this convolution product gives algebra structure on CG. So let us verify one by one. So as I said before, it is easy to see that this delta E indeed an unit element in CG, and if we take this delta functions delta G, so they indeed behave very well with respect to the group multiplication. So maybe I will leave that to check. So for G H in capital G, so if we take this delta G star delta H, so this is the multiplication convolution product that we have defined on this CG, and this actually reflects the group product that we have on G. So basically delta G star delta H is equal to delta G H. So this is something we have. So now using this we are going to actually verify that this star is indeed gives us associative multiplication. So for that, so let us actually see like how one can simplify the product. So if we take two functions a b in CG, so then one can write this a as summation a of g delta g, g in g, and similarly b as summation b of g delta g, g in g. So now if you just go to the definition of a star b, so then we get that using a distributive law, so this is going to be equal to summation g h in g a g b h delta g star delta h, which is exactly equal to summation a g b h and delta g h in g. So which tells us that indeed a star b is given by summation x in g. You call this is x. So then it is clear that if this is x, then this sum is going to be summation y runs over in g such that a of x y inverse b y, and then you have this delta x here. The coefficient of delta x is exactly given by this a star b of x. So that is how actually we are going to get the definition of a star b. So this computation indeed tells us that the convolution product of functions indeed motivated from the group product that we have among the group elements, and that is indeed reflected on this delta g and delta h. Okay. So now we are ready to check indeed CG is a ring with addition taken pointwise and convolution as multiplication. So moreover, we have this delta E is the multiplicative identity. So that is, I am going to leave it to you to check. So the exercise is that delta E is the multiplicative identity, so that you can check. So now we will check that it is indeed associative. So that is the bit involved checking, maybe I will do it now. So associativity follows from the following computation. So, you take A, B, C from elements of CG. So, then there are two ways to actually take the product among these elements. So, you can take A star B star C and then A star B star C. So, we were asking whether these products are equal or not. So, let us directly compute it at the value of x and then see. So, on the left hand side what we have A star B star C and evaluated at let us say some x. So, this is going to give us. So, first we will use the definition of. So, this is like some f, this is like some g. So, then if you use the definition, then you get this is exactly summation y runs over in g, then f of x y inverse, which is A star B of x y inverse, and then you have C of y. So, this is what we have, which again you can rewrite using the definition of this A star B. So, if we replace this with the definition of A star B, then you can see that this is summation y in z, y in g that we will keep, and then this we want to replace. So, which is summation z in g A of x y inverse z inverse and then b z, and then we multiply by C y. So, now if you just collect them together, so what we are going to see, or we can also actually do the change of variable, maybe we will do that. So, let us say we do this following change of variables. So, we fix this z y as u, take u to be z y. So, I want to replace this. So, then it is clear that u inverse is y inverse z inverse. So, in particularly z is going to be u inverse u. So, from here I want, so from here I want z. So, z is going to be u y inverse. So, now if I use that substitution, then this one I want to replace. So, this is replaced as u inverse, and then z will be replaced as u y inverse, and then we will keep the y. So, then that summation is going to be exactly equal to summation y in g, summation u in g, A x u inverse, b u y inverse, and then C of u. Now, if you just collect, if you fix u and then collect y, so that means you just interchange the sum, summation u in g, A x u inverse, and then collect the y in one sum, b u y inverse, C of y. So, then you can see that this is exactly equal to, so this is going to give us b star C of u. So, this is summation u in g, A of x u inverse, b star C of u, which is exactly equal to, now if you use the definition for A star B star C, then you can see that this is exactly A star B star of C of at x. Okay. So, which is the right hand side. So, we started with the left hand side, which is A star B star C at x, okay, for x in g. So, then we conclude that which is same as A star B star C of x. So, that proves that the associativity is true, and remaining properties like distributive law and so on, they all will be verified in similar fashion. So, I am not actually going to do that, I will leave it to you. So, that actually tells us that this CG with respect to this pointwise addition and convolution product makes this into a ring. So, in particularly along with the vector space structure, the CG becomes an C algebra. Now, it is not very hard to see this algebra CG naturally isomorphic to the group algebra CG. So, recall that the group algebra is the formal sum of AGG with the coefficients AG and C for all G and G, and the group multiplication on G will be extended to multiplication on CG, that makes CG into an algebra, and this function space with the convolution product is indeed isomorphic to CG. So, we also have another product coming from the product on the complex space, and that product also will actually make CG into a ring, but you can see that that product is going to be very different from the convolution product. So, we also have what is called this pointwise product on CG. Okay. When you are thinking as the group algebra, we do not see the pointwise product, but when we think it as complex valued functions from G, so then we can talk about pointwise product. So, how this is defined? Given A B in CG, define A dot B of x to be just A of x B of x for all x in G. So, this is something that is obtained using the structure of the complex numbers. So, complex numbers are indeed vector space, it is an C algebra. So, using the addition we get the pointwise addition on CG. Similarly, we can also get pointwise multiplication. But this product is indeed very different from the product that we have already constructed, that is the convolution product. That is because since C is commutative, that will imply that this CG with this pointwise addition and pointwise multiplication. So, this is going to be always commutative. Okay. So, this is pointwise addition and this is pointwise multiplication, and this ring structure is always commutative because C is commutative, and you can see that CG with pointwise addition and the convolution, this is far from commutative if G is not abelian. Okay. Indeed, this CG is abelian, CG is commutative if and only if G is abelian. That is something you can directly check. Maybe I will leave it as exercise that CG plus star is commutative ring if and only if that G is abelian. So, when G is not abelian, definitely we are not able to compare this if G is not abelian. But then you can ask like what happens if G is abelian. So, these two algebras, are they same or different? Indeed, one can prove that for finite abelian groups, these algebras are indeed isomorphic when G is abelian, finite abelian group. So, there is no big difference between the convolution product and the pointwise product as far as the algebra structure concerned. So, how these two structures will be connected? So, they will be connected by this Fourier transform. Okay. So, let me define that and then prove that result. But before that, let us actually justify the space of class functions, why they were denoted as the center of this CG. So, the notation CG ZCG. So, this is the space of class functions. So, like I said, we use this notation Z to indicate that this space is indeed the center of CG. So, that is what happens indeed. So, let me write it as a proportion. The proportion is that this Z of CG is the center of CG. So, when I say CG, then I am talking about the convolution product. Okay. G is any general group, and I am talking about the convolution product on CG, unless otherwise it is specified. So, what is the meaning of this? That means given any class function that commutes with all elements of this CG. So, for all f in Z CG, we have A star f equal to f star a for all A in CG, and conversely, if f in CG satisfies A star f equal to f star a for all A in CG, then that would imply that f is in ZCG. Okay. And it is not difficult to see that if f is a class function, then it must be in the center. So, maybe let us check that. Okay. So, let f is in the class set of class functions. So, that means we know that f of g h g inverse is going to be f of h for all g h in G. So, this is how it is defined. So, now let A in CG and then start doing the calculation. A star f at x, by definition it is going to be summation y in G A of x y inverse f of y. So, which is going to be equal to summation y in G A of x y inverse. Now, we can replace this y by the conjugate of y. So, f of x y x inverse. So, now since f is a class function, so now what we will do, we will just set Z to be x y inverse. So, we have to do this change of variable. We set this x y inverse to be Z. So, then this equation can be rewritten as follows: summation Z in G A of Z. So, then so this is going to be our Z inverse. So, this is f of x Z inverse. So, now if you see this, this is exactly equal to f star of A of x. So, that means A star f is same as f star a for all A in CG. That tells you that Z of CG is in the center of CG. Now, let us start with f that is in the center. So, let us say f in CG such that f star a is same as A star f for all A in CG. So, now we want to verify that f of g h g inverse is equal to f of h, which is equivalent to saying that f of g h equal to f of h g for all g h in G. Okay. Need to verify this. Need to verify this. So, now we start with the left hand side f of g h. So, which is exactly equal to summation. We write it in terms of the delta function. Then if we write it in terms of the delta function, which is exactly equal to f of g y inverse delta h inverse y, y runs over G. So, the delta function when y equal to h inverse will give us this 1, this part is 1. So, that tells you that this f of g h can be written as this. That means, this is exactly equal to f star of delta h inverse of G. but since f commutes with all elements of CG, so this can be replaced, f star delta H inverse can be replaced as delta H inverse star f of G. So, now if we use the definition, then we can see that this is exactly equal to summation delta H inverse G y inverse f of y and y runs over G. So, now you can see that this element is going to be exactly 1 when G y inverse is H inverse. G y inverse is H inverse is equivalent to say that, so we have fixed G and H, you can see that this is same as saying H G equal to y inverse. So, other than that, sorry, H G is equal to y, yeah, H G is going to be just y. So, whenever this H G is y, that is the only time this value is going to survive. So, that tells us that this is exactly equal to f of H G. Okay. So, we started with f of G H, we wanted to prove which is equal to f of H G, that is verified. So, that means the space of class functions, they are indeed the center of this CG. So, with respect to the convolution product. Okay. So, now the Fourier analysis on finite abelian groups can be done as follows. So, we just recall what is the dual group. So, let us say now G is finite abelian group. So, G hat is nothing but the one dimensional characters from G to C cross. So, we already proved that G is isomorphic to G hat as group. So, there is no difference between G and G hat. So, this is indeed the dual group. So, this is indeed what is called the dual group. And recall what is the multiplication that is defined on the dual group. So, given chi and theta in G hat, chi times theta is defined to be just the pointwise multiplication. Chi theta of G is just chi of G times theta of G for all G in G. So, this is how the multiplication is defined. Okay. So, G hat is an abelian group of order cardinality of G, and G and G hat, they are isomorphic. Now, what is the the additive identity and the inverse? So, if you recall the chi 1 of G, which is the constant function for all G in G. So, this is the identity element inside G hat, and given chi in G hat, the chi inverse of G indeed defined to be chi G of inverse. So, which is the dual of the representation. So, it corresponds to the dual representation, which is exactly corresponds to the chi G bar. So, this is follows from the fact that chi is unitary. So, this is, we already know it is unitary because it is a function from G to C cross. So, now with this we can actually work with functions on G hat. So, that can be replaced on the right hand side. Okay. So, if we go back to the cyclic group, so we had the Fourier transform defined from the function space from Z modulo n Z to C to again Z modulo n Z to C. So, here we define. So, now what we want to do when we go to finite abelian groups, we want to replace these spaces as follows. So, we want to replace it by Cg to Cg hat. So, the Fourier transform will be defined from these spaces. So, that is actually indeed clear from the fact that the G hat can be identified with the function chi k that we defined for Z modulo NHN. So, anyway, I am not going to repeat that. So, let us directly define the Fourier transform. So, now given a complex valued function f from G to C. So, here G is finite abelian group. So, given this we want to define, so this capital T is called the Fourier transform. So, this actually maps this f to f hat. What is this? This is a map from G hat to C. It takes the value f hat of chi. So, if you recall, the chi's, they will form an orthonormal basis. So, all we need to record f is the inner product between f and chi. So, we just record that using the Fourier transform. So, this is going to be the cardinality of G inner product f chi. Okay. So, this is exactly equal to the summation f of x chi of x bar, x comes from G. So, since this f hat defined using the inner product, and the inner product is linear in the first variable. So, it is clear that this map T is indeed linear map from Cg to Cg. Okay. So, indeed we are going to say that, sorry, Cg hat, indeed we are going to say that this is indeed isomorphism, and these f hat of chi, they are called indeed Fourier coefficients of f. So, the Fourier inversion tells you that. So, this given f hat, one can recover f completely. So, before that, let us see what happens to these characters, irreducible characters. So, if I take chi theta coming from G hat. So, both chi and theta, they are functions from G to C cross, but C cross lives inside C. So, they are complex valued function. So, in particularly we can talk about the Fourier transform of that. So, if you evaluate chi hat of theta, so then by definition it is going to be cardinality of G, the inner product chi comma theta. So, now using the orthogonality of irreducible characters, you can see that this is exactly equal to the cardinality of G if chi equal to theta and it is 0 otherwise. So, that means chi theta chi hat is indeed very much closely related to with the delta function. So, the orthogonality relation indeed gives us that chi hat is equal to the cardinality of G delta chi, because that is how this function here it is behaves. So, now the Fourier inversion is easy to state and prove. You can see that the map that we defined T from Cg to Cg is an isomorphism, sorry, G hat isomorphism of vector space. So, what does it mean? So, if f is given in Cg, so then we want to recover f completely. So, the one can completely recover f using the following formula from f hat, that f equal to 1 divided by cardinality of G summation chi in G hat and f hat of chi chi. So, this formula tells us that how to recover f from f hat. So, this is straightforward computation. So, because you can write f as summation f chi 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 in G hat, because the elements of G hat they form an orthonormal basis for Cg hat, and which is equal to 1 divided by the cardinality of G summation the cardinality of G, the inner product f chi comes from G hat. So, now by definition this is replaced as f hat of chi. So, that tells you that this formula is true. So, that means this is indeed an isomorphism between CG and CG hat. Now, it is not hard to see that this is indeed gives us algebra isomorphism. On the right hand side we take the pointwise product, but on the left hand side we take actually the convolution product. So, let us look at this map T from CG to CG hat. So, now let us make it very precise. This is CG addition star, this is what we have. Here we take it to be CG hat addition and then we take this pointwise multiplication. So, this is pointwise multiplication and this is convolution product. Okay. So, now it is easy to see that this map T which takes f to f hat, this is a linear invertible transformation, because both sides we have actually same dimensional space and Fourier inversion tells that given f hat you can recover f. So, that indeed says that this is indeed a vector space isomorphism. Now, what we want to check, this indeed actually takes the convolution product to the pointwise product. So, that is the only thing that remains to check. So, let us check, that means given A B inside CG. So, we have that A star B hat is indeed given by A hat times B hat. So, this more or less follows from the definition. So, let us verify directly. So, if we take A star B hat and apply chi on that. So, by definition this is going to be n times inner product A star B chi. Now, we already know that what is the inner product. This is going to be n times 1 by n summation A star B of x and chi of x bar x in G. So, this is by the definition of the inner product. So, n get cancelled. Now, if we use the definition of this convolution product, so then we get that this is exactly equal to summation x in G and we keep this chi of x bar and then we replace this A star B x to be A of x y inverse B y and y comes from G. So, now if you simplify then you can see that A star B hat of chi is going to be exactly equal to summation B of y y in G and then summation A x y inverse chi of x bar where x comes from G. So, now what we do, we just set Z to be x y inverse, that means x is equal to Z y. So, if we replace this Z equal to x y inverse, so then we get exactly A star B hat of chi is equal to summation B of y y in G and then summation A Z and then chi of Z y bar and Z runs over G. So, now this you can again simplify that summation B of y chi of y bar, because chi is again character. So, it splits. So, then this is exactly A of Z chi of Z bar where Z runs over G and y runs over G. So, then if you again simplify, you get that A star B hat of y is equal to summation A Z chi z bar, z runs over in G, and then summation y in G, b of y and chi y bar. So, we are just rearranging the terms. So, that tells you that this is inner product and this is the inner product. So, that means this is going to be n times A chi. So, this is the inner product n A chi, and then this is inner product n B chi. So, basically this is exactly A hat of chi times B hat of chi. So, that tells you that A star B hat of y chi is exactly equal to the pointwise product A hat chi and B hat chi. So, that means the Fourier transform actually converts the convolution product into the pointwise product once you go to the dual group. So, that is what happens at the level of abelian groups. So, we need to kind of modify things so that we can actually do the same Fourier analysis to the general non-abelian groups. So, for that we need to actually replace the dual group by something else. So, that we will actually see what to do with that in the next class. I will stop here. Thanks.